Okay. Today I want to construct a qubit spline function. Qubit spline function is a piecewise polynomial function. So over each interval, spline function is a polynomial. Qubit, the polynomial, the degree is free. The second topic, I present the dimension of this space. This notation is the set of all spline functions of degree k. Put all the spline functions together. We have a set. The notation is this. Then what is the dimension of this space of this set? Take a review about a spline function. Spline function is a piecewise polynomial function. Precisely given a non-negative integer and n plus 1 lots. These lots are in increasing order and between A and B. A, B, it is an open interval. Yeah, take a look at this diagram. A, B, open interval, and all the lots between A and B. Then a spline function of degree k associated with the given lots is a function S. S, the first letter of spline. It's a function S. S is smooth of order k minus 1. Smooth when a curve has a corner, not smooth, low corner. Okay. And over each of these intervals, from the first interval, pay attention, is from A to T1, not A to T0. From A to T1, S is a polynomial, degree not greater than k. And from T1 to T2, this interval, the left endpoint is included, right endpoint not included. From T1 to T2, it is a polynomial of degree not greater than k, and so on. The last interval is Tn minus 1 to B. Yeah, Tn, this point, to B. Over this interval, it is a polynomial. Yeah, this is the definition of a spline function. Now, the first topic today, I want to construct a qubit spline. That means that degree of the polynomials is free, qubit spline. Okay, I want to construct a qubit spline. Now, topic one. Okay, given a table, this table, the lots T0, T1, T2, and Tn, corresponding to the lots, I specify some values: beta 0, beta 1, beta 2, and beta n. The beta values, they are not the values of some function. No, yeah. Let me draw a diagram about these points. XY plane. XY plane. the lots are on the x-axis. Suppose the open interval AB is here. T0, T1, T2. This is a TK minus 1, TK, TK plus 1, and so on, and so on. Okay, let me plot these points on the XY plane. When T0, beta 0, say this point. T1, beta 1, this point. And this point. This point. This point. This point here. Okay. Yeah. The beta values are just randomly, okay, pick, okay, just randomly pick. Now, what I want to do, I want to construct a spline, a cubic spline. Okay. I want to construct a cubic spline S such that S at T K is equal to beta K. I want to join these points. Yeah, join these points with polynomials of degree 3. Okay, I want to find a cubic spline to pass all these points. These points, quite arbitrary pick. Okay, according to the definition of spline function on each interval. Okay, let me write cubic spline explicitly on over each interval as follows. Over this interval, the first interval is from A to T1. Yeah, A to T1. Yeah, here. A to T1. A to T1. It is a polynomial of degree 3. This polynomial passing this point and also this point. Okay, this point. Right. Over this interval, let me cubic polynomial A0 x to the third plus B0 x squared C0 x then D0. Okay, what is A0, B0, C0, D0? I will determine them. Okay, so that this polynomial passes this point and also this point. Then over the second interval is from T1 to T2. S is a cubic polynomial. The polynomial is A1 3 B2 no not B2 B1 x squared C1 x then D1 over the second interval. Yeah, it is a cubic polynomial. And so on. Over the last interval is a Tn minus 1 to B. Let me, okay, this is a Tn minus 1, then Tn here. The points from this table is say here. Okay, now I want to find a polynomial through these 2 points. Through these 2 points. Over this interval, let me assume the cubic polynomial is a(n minus 1), x3, b, bn minus 1, x squared, cn minus 1, x, then dn minus 1, dn minus 1. This is S. This is S. Okay. Each cubic polynomial has 4 coefficients. So in total, how many coefficients I need to determine? We need to determine how many polynomials we have here. N polynomial, right? From A0, A1 to an minus 1. N polynomials. Each polynomial has 4 coefficients to determine. So in total, okay, there are 4 times n coefficients to determine. For n, so many coefficients to determine. We need 4n equations in order to determine these coefficients. By assumption, S is cubic spline. Cubic spline, okay, since S is cubic spline, by definition, S derivative of S, second derivative, continuous, right? Are continuous over the open interval A to B, continuous by definition. Okay, now I use these conditions to establish 4n equations to determine the 4n coefficients. Okay, number one, we want the cubic spline at each log is beta k. Yeah, we want the cubic spline. Interpolate this table or pass the points in this table. So therefore, from this condition, I can have some equations. Let's focus on let me redraw a diagram. This is X. This is a Y. Suppose TK, this point is here. TK plus 1, this point is here. Then over this interval, we have cubic polynomial. How about let me give a name to this portion of the graph of S. Let me call it, because this portion corresponding to the interval from TK to TK plus 1. So let me give a name. Say, how about SK? SK is a polynomial. It is AK coefficient, 3, BK square, CK x dk. All right, now because we want S at TK is beta from this equation. This equation, this leads to the following equations. Sk at Tk should be equal to beta k. You agree? Right? At Tk, this point, S, the value is beta k. So Sk, the value at Tk is this. And Sk at Tk plus 1 should be beta k plus 1. Where k is from 0. When k is 0, it is polynomial. When k is 1, is from T1 to T2 is this polynomial. When k is n minus 1 is this polynomial. Okay, so therefore k is 0, 1, 2 to n minus 1. Okay, now, how many equations from this condition? Okay, how many? One equation, plug in Tk in x here, then set this to beta k, one equation. Plug Tk plus 1 here and set it to beta k plus 1. So one equation, two equations for each k. But k goes from 0 to n minus 1. So in total, 2n equations. We have 4n coefficients to determine. Now we have 2n equations. Now, how about other equations? Let's see. This is number 1. Yeah, actually, when Sk satisfy these two conditions, then automatically these two equations implies S is continuous on AB. Yeah, when Sk, yeah, this guy, this portion satisfy this condition and this condition, then the whole curve from A to B, the whole curve S must be continuous. All right, now the second condition. Derivative of S. Derivative S. Second derivative continuous. Continuous on interval AB. What it means? That means continuous. Okay, that means S derivative k minus 1. Sk minus 1, where? Sk minus 1. Okay, let me pick this part. Tk minus 1. Then the polynomial over the interval from Tk minus 1 to Tk. Yeah. This is Sk minus 1. And the polynomial is Ak minus 1 x free, Bk minus 1 x squared plus Ck minus 1 x plus Dk minus 1. Hey, because this guy continuous, so Sk minus 1 derivative at Tk should equal to Sk derivative at Tk. Yeah, because this guy is continuous. Then K What is K? K is from 1, not from 0, because when K is 0, this is S -1, low S -1. The first interval is corresponding to S0. So K is 1, K is 2, and also K is n-1, right? n-1, yeah. This part, Tn-1, yeah. When K is n-1, Tk is Tn-1, yeah. So at this point, first derivative is continuous. Yeah. Actually, T1, T2 to Tn-1, we call them interior lots. Here we have n-1 equations. From the continuity of second derivative on K-1. Yeah, take second derivative on this guy. Then at Tk, because continuity should equal to Sk, yeah, this portion, Sk. Second derivative, evaluate at Tk, they should be equal because continuous. Continuous. Right. Yeah. So how many equations we have? Here, Sk, yeah, these two equations guarantee S, this function, continuous. And this equation guarantee derivative continuous. Some people may ask me why K cannot be 0. Because when K is 0, T0, S is always continuous. Because from A to B, from A to T1, this is a polynomial, always continuous at T0. So we don't need to worry about T0. And again, and also, we don't need to worry about at the point Tn, because from Tn-1 to B, a single polynomial, of course, continuous at Tn. So what we need to worry about is continuity at T1, T2, and Tn-1. Yeah. How many equations we have? Here we have 2n equations, and here we have n-1 equations, and here we have n-1 equations. So in total, we have together 2n plus n-1 plus n-1. We have 4n minus 2 equations. So 4n coefficients. Now we have 4n minus 2 equations. So then that's not enough to completely determine the 4n coefficients. We have 2 degrees of freedoms. Two degrees of freedoms remain. What it means? It means that 2 of the 4n coefficients can be assigned values arbitrarily. We have 2 freedoms. Okay. Yeah. So 4n coefficients there are two coefficients. We can arbitrarily assign values to them, and then the remaining coefficients determined by these 4n minus 2 equations. Now, let me, in the following, let me completely determine the coefficients. Okay, let me set S second derivative at tk k from 0, 1 to n plus 1 loops. At each lot, second derivative, I set the value to be ck. What is ck? I don't know at this point. ck will be determined. All right. Okay, then let me focus on this polynomial. This polynomial is defined on this interval. All right, then take second derivative on this polynomial. Then second derivative on sk and evaluate at tk. It should be ck. Second derivative at sk, evaluate at k plus 1 is ck plus 1. Yeah, because s second derivative of s continuous, we have these two conditions. Yeah. If these two conditions are satisfied, this will imply the whole curve second derivative is continuous on the interval AB. Okay. SK, polynomial of degree 3. Now take derivative twice. We get polynomial of degree 1. Yeah. Note, second derivative of SK is polynomial of degree 1. Polynomial of degree 1, what is that? It is alpha x plus beta. Polynomial of degree 1. Now, from these two equations, I can completely determine alpha and beta. Let me give a name to these two conditions. Let me call them 1. Then 1 condition, the two equations in 1 will lead to second derivative of k. It is a linear polynomial. Two equations completely determine alpha and beta. Then we get this. Okay, ck over hk. By hk, I mean tk plus 1 minus tk, and times tk plus 1 minus x plus ck plus 1 over hk and x minus tk. these two equations completely determine a polynomial of degree 1. Yeah, the polynomial is this. Okay. Now, take integral on this equation to recover Sk. Okay. Take integral twice on this equation. Then we have Sk. I want to find Sk. Then Sk is Ck 6hk Tk plus 1 x to the third plus Ck plus 1 6hk x 3, and then C. Take integral once we have an arbitrary constant in the expression, in the resulting expression. That arbitrary constant is called constant of integration. C, arbitrary. X minus Tk. And D, arbitrary, because I take integral twice. Tk plus 1, and then Sk. Hey, where Ck, C, D, constants of integration. How to determine C and D? Recall that S at Tk is beta k. S at Tk plus 1, beta k plus 1. I use these two equations. I can determine C and D. Okay. Let me give a name. Say, call this number 2, equation 2. Use the equations in equation number 2. I can determine C and D. We can tell C and D. We can tell C and D. So Sk is Ck 6hk Tk plus 1 minus Ck plus 1 6hk x Tk. And now what is C? C is this number C, beta k plus 1 over hk minus Ck plus 1 hk, then over 6, then times x minus Tk. Then what is D? D is beta k over hk minus Ck hk over 6 times Tk plus 1 minus x. Yeah. This is the polynomial over this interval from Tk to Tk plus 1. Okay. Now, the next question is how to determine this guy. We don't know this guy yet. If I know this guy, then I know Sk, because Sk involves Ck plus 1. We don't know these two quantities. Okay, now let me determine Ck plus 1. What conditions so far we have used? We have used the continuity of S, this condition, because when these two equations are satisfied, S continuous at the lot. When these two conditions here, when these two conditions are satisfied, S second derivative is continuous on the interval A to B. So far we haven't used is the continuity of the first derivative. So let me use this condition to find CK. Okay. Okay. Next, we use the continuity of first derivative to determine CK. Okay, to determine CK. Go back to this diagram. Go back to this diagram. Here, go back to this diagram. Derivative is continuous if derivative continuous at the interior lot, then the whole curve S will be continuous. Will be continuous. Okay, now next, okay, the continuity of derivative, first derivative, leads to the following equation. Sk minus 1 derivative. Yeah. Sk minus 1 is this portion. Derivative. Sk is this portion. Derivative. Because they're continuous, their value should be equal at Tk. So we have Tk should be equal to Sk derivative at Tk. Tk, what we concern is interior lot. That means that K is 1, 2, and N minus 1. When K is 0 at T0, because from A to T1, it is a single polynomial. That polynomial, of course, first derivative is continuous at T0. And similarly, at Tn, from Tn minus 1 to B, it is a polynomial, a single polynomial. Take derivative, the derivative, of course, at Tn. So what we concern is interior lot from 1 to n minus 1. So yeah, from 1 to n minus 1. Yeah. We have this equation. Now we have Sk. Sk is this. Sk is this. Take derivative on this guy. Take derivative on this guy and evaluate the derivative at Tk. Yeah. Right. Take derivative on the guy and evaluate at Tk. Then we have this expression. Ck unknown. Hk over 6. Ck plus 1 unknown. And then beta k hk plus beta k plus 1 hk. Yeah. This is this guy. Yeah, this guy. Then how about Sk minus 1 derivative? In this equation set K, replace K by K minus 1. Then we have the expression for S K minus 1. Take derivative and then plug in TK. Then S K minus 1 derivative at TK is HK minus 1 6 C K minus 1 plus HK 3 CK minus beta K minus 1 HK minus 1 plus beta K HK minus 1. Now set this guy equal to this guy. We have an equation. Therefore, set this equal this guy equal to this. Then we have an equation. CK minus 1, CK plus 1, unknowns. Now I move the unknowns to the left side, constants to the right side. Then I have this equation. That implies this equation. HK minus 1, CK minus 1 plus 2 HK minus 1 CK plus HK CK plus 1. Then constants to the right side. Uh, 6 over HK beta K plus 1 and 6 HK minus 1 beta K minus 1. Okay. This is for 1K. Now K is from 1 to N minus 1. So here we have N minus 1 equations. How many unknowns? When K is 1, C K minus 1 is C0 unknowns. C0 unknown. C1 unknown. And when K is N minus 1, there is a CK plus 1. K is N minus 1, so Cn unknown. So N minus 1 equations. N plus 1 unknowns. We cannot completely determine the unknowns, but we can, because we have 2 degrees of freedom. 2 of the unknowns can be arbitrary assigned values. Yeah. Say, let me assign C0. We call that, what is C0? Derivative at T0. Yeah. This is a derivative at T0. Say I can arbitrarily assign values to C0 and Cn derivative at Tn. Say according to the book, in this section we assign 0 to C0 and then 0 to Cn. Yeah. Then if I assign this guy 0, then N minus 1 equations can determine N minus 1 unknowns. There is a term for these 2 conditions. The resulting cubic spline is called, when second derivative at the log T0 and the log T1 Tn are 0, that cubic spline there's a name. Let me see how the book called them. It's called a lateral cubic spline. If you actually you can arbitrarily assign values to C0, Cn. For other values, the resulting cubic spline, not lateral. Okay. Okay. Now, assign 0 to CK, C0, 0 to Cn. Then this n minus 1 equations in matrix form. In matrix form, okay. It is this. U1, I will tell you what is U1. H1, U2, I will tell you what is U2. H2, U3, H3, and so on. It turns out that the coefficient matrices are tri-diagonal matrices. H n minus 2, minus 3, U n minus 2, H n minus 2, then H n minus 2, U n minus 1. Yeah, coefficient matrices. The unknown is C0. We have set it to 0. So the first unknown, C1, C2, and Cn minus 1. And the right side is V1. What is V1? I will tell you. Briefly. Vn minus 1. Yeah. Okay, now where? Hk, we have defined it. It is this number. Then what is UK? Yeah, UK is this number. Let me define BK. Beta K plus 1. Beta K. Okay, then now V. What is V? V is BK. Yeah, define here. Minus BK minus 1. So solve this linear system for C1, C2 to Cn. Then plug in the result in the C here. Then we get SK. We get SK. Yeah, because K is from 0 to n minus 1. So here, each cubic polynomial has been determined. Each polynomial has been determined. That means that the whole function S is determined. This process of constructing a cubic polynomial works well, but tedious. So clearly, this construction method is not easily to be extended to construct spline function of degree higher than 3. So in next section 6.6, we will develop new approach to construct a spline function of degree higher than 3. Okay. Not follow this approach, too tedious. The final remark about cubic spline functions. Okay. These points, n+1 points, arbitrarily assigned. So here we have n+1 freedoms. And we call that C0, Cn. We can also arbitrarily assign values to these two guys. So in total, we have n+3 freedoms to determine a cubic spline function. So therefore, as a result, Sn3, this is the set of all cubic spline functions, or it actually, this is a space. Yeah, there are some conditions for a set to be a space, but this set satisfies those conditions. Actually, this is a space. Because n+3 freedoms to determine one cubic spline. So this space has dimension. Dimension n+3. The dimension of this space is n+3. What it means? Each basis of Sn3 has elements. Yeah. Each basis contains n+3 functions. Okay. This is a remark about this set. Let me stop here.